Right, so the next speaker is giving his goodbye talk here, I guess.
You could say so, yes. Okay, thanks.
It's not inaugural, it's the co-inaugural.
I forget.
Suddenly there's a lot of pressure.
Yes, it's the ex-inaugural.
Yeah. I want to talk about some stuff that I did recently on states and measures. It's mostly about quantum states, but there are lots of analogies with classical physics and classical states, and so I just decided to call it states and measures. Yeah, there are these two nice quotes, a pretty heavy one from Bertrand Russell, which I will not read aloud, but I think I'll go with more. This is a very good quote, which actually seems to be authentic. So, the work I'll be talking about comes from the topos approach to physics, which of course was initiated by Chris and Jeremy a while ago, and this is what I'm working on, and this comes from, well, I don't want to say it comes from quantum gravity, it comes from the fact we don't have quantum gravity, we want to do something, and we have lots of conceptual problems, and we have conceptual problems already in the standard quantum theory itself. Most work in the approach has been done on quantum theory, and in particular on what you could call algebraic quantum theory, where the algebra observable of the quantum system is some phenomenon algebra. So we assume that we always have such a phenomenon algebra n, and I'll say a bit more about these guys. Particularly I want to talk about states on phenomenon algebras. And this is now, well, I would say function analysis 101, a few basic facts about phenomenon algebras and states, mostly to settle the notation and also to shift perspective slightly away from vectors in Hilbert space. Yes. You see how they fit in, but a state is, well, it's something slightly different than a vector in Hilbert space. So every phenomenon algebra, n is well, a weakly closed subalgebra of some b of h, we know bounded operators in Hilbert space. If you don't know this stuff at all, you can always think about all bounded operators in some Hilbert space, finite or infinite dimensional. Every phenomenon algebra has a unit element, and this is always the identity operator in our Hilbert space. And then within the algebra you have the self-adjoint elements, right, and with this subscript SA. They form a real vector space, and they of course are representing physical quantities. Now a state on phenomenon algebra is a positive linear function. It takes elements of the algebra into the complex numbers, and it's normalized. And of course, if I apply this to self-adjoint elements, I get real values. And if I have two states, row 1, row 2, and have some number between 0 and 1, then I can form this convex combination, a row 1 plus 1 minus a row 2. This is another state. So I get a whole convex set. And this is written as S of n. This is an important object. This S of n, this gets a topology, the so-called Greek star topology. This is called the state space of the phenomenon algebra. We'll see in a second how, well, vectors in Hilbert space give us such things. And then it's a convex set, and you can think, well, it has extreme points. Those are the pure states. For the case of, well, b of h, the pure states will be the vector states. And there are also states which are not extreme, these are mixed states. So here are the vectors in Hilbert space. Physicists very often say, well, we have some Hilbert space H and psi. What they actually are doing, they're calculating expectation values. So what they do is they take the state psi and form these expressions psi a psi for a self-adjoint operator, some other operator from the phenomenon algebra. And this means you actually treat your vector psi as being a linear functional. That's what the state does. And then it's very simple because it's a linear functional. We have the following property for every state. Apply state rho to the sum of pairwise orthogonal projections, finitely many. Then I can as well take the sum of rho and apply to the states. So this is just linearity. But there are particular states where I can take infinite families or arbitrary families of powers of orthogonal conjunctions. And still this additivity holds. It's not the case for every state, but for some states it is the case, and those are called normal states. For example, these vector states are normal states. Normal states can be characterized with strong theorems. Every normal state is a convex combination of vector states. So I can write each normal state row in this form where the coefficients just sum up to 1. Mostly in physics we actually concentrate on normal states. There are some situations, K-ness states, so where we want non-normal states. And then there's this form which should be even more familiar to physicists. A normal state can also be written as trace rho tilde A. And rho tilde here is a positive trace class operator of norm 1. This is what physicists call the density matrix. So we see this notion of state that I'm talking about. This encompasses the usual notion of, well, vector and Hilbert space, all mixed states, and even more general things like K-ness states. So this is the most general state. Every state of a quantum system is of this form. It's a state on the phenomenon algebra. Okay. This is nothing about topos approach up to this point, but now we start, and now we get context and contextuality into the game. So we have phenomenon algebra, and we just look at its abelian subalgebras. So there's this set of abelian subalgebras which we denote as V of n, and V is always an abelian algebra. Okay, it's non-trivial means not just the multiples of the identity operator and what co-unital is a word I made up. They all have a unit, of course. I just mean they all contain the identity operators. They all have the same unit. Okay. And this is just a formalization of what Terry would call a context. It's an abelian subalgebra of some non-abelian algebra of physical quantities. And this is why we call these algebras also contexts, the abelian ones. Then there's this nice theorem, and that's actually not very surprising. It's just, again, a mathematical formalization of a fact that it should somehow be clear intuitively. If I just look at one abelian algebra, everything looks like in classical physics. In particular, every algebra, every abelian algebra V has what is called a Kochen-Specker. This is just some topological space. And I can write all the operators in the algebra just as functions on this space. In particular, the self-adjoint operators become real-valued functions. And this is just like classical physics, where you have a state space for your system, and your physical quantities are real-valued functions on that space. Okay, these Kochen-Specker, they have this notation sigma V. The index V just tells me, okay, this belongs to the algebra V. And I get this for every abelian subalgebra, so I have lots of these Kochen-Specker. And yeah, here's the physical interpretation, is what I said. And the idea in the topos approach is the following. We know that there is nothing like the Kochen-spectrum for the full non-abelian algebra. It just works for abelian algebras. But we still want some structure for the full non-abelian algebra. The idea is actually quite simple. One collects all these local things and all these abelian parts. You have a Kochen-spectrum, collect them into one big structure. And this big structure is not a set anymore. It's something more complicated. It's a presheaf. And actually it's not very hard to see how this works. You do the following to every abelian algebra V. You just assign its Kochen-spectrum. And then, oh, I didn't say this up to this point. We equipped all the set of all abelian subalgebras with a very simple poset structure. We just say inclusions of smaller subalgebras into larger ones give us a poset structure. So now I have to say something. When I have such an inclusion of, let's say, V prime into V, then I need a function from what I assign to V actually to what I assign to V prime. So I will have something which turns around the arrows. And it's very simple. I didn't actually say what these elements look like. We don't have to worry about this too much. So an element here in this Kochen-spectrum, the big algebra, can just be made into an element of the spectrum of the small algebra by restriction. This is a well-known thing in function analysis. You can do it that way, and that's what we want to do. And people who know a bit of category theory will see it's a contravariant functor from this post set of abelian subalgebras to sets, and that's what is called a presheaf. Okay, but all this technical stuff just means I have for every abelian part, every commutative part, which I can see as one classical perspective of my quantum system. I do have a state space, and now I collect them into one big thing. But it's not just a disjoint union, I also have some relations between the relations I encoded here in this, what I do for the inclusions in this kind of functions. These functions are continuous and surjective and also closed and open, so I have lots of good properties. I now have something which you should think of mathematically as something like the spectrum of this nonabelian algebra. There would be more work to do. This is mathematical side, it's not a generalization of Gauss-functionality. There's lots of stuff missing. But still, it's something like a spectrum of this nonabelian algebra, and physically, it is something like a state space for the quantum system, but it's not a space anymore, it's this presheaf. Okay, and this presheaf, which we call the spectrum presheaf, actually plays the role of the state space of the quantum system. And it turns out, you can ask, now in categorical terms, does it have points? And it turns out, interesting, it doesn't have points, it doesn't have global elements. This is the posh way to say that. This is actually exactly the Kochen-Specker theorem. So you may want to think about this presheaf sigma as some kind of non-commutative space, a non-commutative character being expressed by the fact that it has no points. The rest of the talk, and that's actually all this was preparation, the rest of the talk I want to show how this thing, which I say is like a state space, how does it relate actually to the state space S of n with these positive linear functionals on the algebra, what people in ordinary quantum theory would call the state space. So how do these things relate to each other? That's the question actually. Okay, I'll skip this part and directly come to part and states and measures. And this is where I want to draw this analogy with classical physics, and it's the following. So let's think about classical physics for a moment. Classical physics, a state, usually you read a text, well, it's a point of state space. That's not actually true. That's the most general kind of state is something else. The most general kind of state of a classical system is a probability measure on the state space. Because you can have some, well, statistical uncertainty also in the classical physics. And it may, of course, be that your state is concentrated at one point. It's the Dirac measure. Concentrated at some point S of your state space. Then you can identify this with the measure itself. At this point, So, the state of a classical system is a measure on the state space. But it's also something else. If I have a measure on the state space, then I get an integral of a certain kind. We know from Rie's representation, every measure on a reasonably well-behaved space gives us an integral on the functions on this space. And what functions do we have on this state space? Well, the physical quantities are real valued functions. Like, I don't know, energy is a function on the state space, or position, momentum, all these things are functions. And now I have a measure on the underlying space, I get an integral on these. So there are two ways of looking at a classical state. It's a measure on the state space, or it's an integral on the abelian algebra of physical quantities. Well, this classical physics, everything will commute, so it's an abelian algebra. Now, what is with quantum theory already saw, we have these positive linear functionals of norm 1, but they are nothing but integrals. So the usual description for a quantum state is it is an integral. The only difference to classical physics, you could say, is it's an integral which now lives on a non-abelian algebra. That's, of course, a big difference, but really formally, there's something which is very parallel to what we do in classical physics. States are integrals. And what is lacking is a description of quantum states as measures, as probability measures on some space. And this is actually where I see the connection with what Terry did, for example, and what lots of people are trying in hidden variable theories. They want to write quantum states or maybe hidden variables with some extra information as probability distributions, or what I would call a measure on some kind of space. But it's not so straightforward as we see, and then there are even strong theorems like the Kochen-Specker theorem telling us we actually can't do it, not in any naive way. So such a thing doesn't exist. So here's what we have.
You can't do it under the constraint of non-contextuality.
Yes, that's what I mean by natural. Okay. Of course, I'm aware I will enter into this discussion, but maybe not at this point. Okay. So you see that there seems to be something missing for the quantum state description. At least, well, at least if you want a one-to-one correspondence between these things. And now, yeah, I will actually show that this gap can be filled in a pretty straightforward way. Actually, we need this object that we define. We need the spectral presheaf, this state space, and we'll show that every quantum state gives you a measure on this thing, which now is not a set anymore, but it's a presheaf. That's okay, but even more interestingly, if you have a measure on this thing, you can get back to a state. You can say abstractly what such a measure is. You don't have to put in the state by hand. Okay. Now, first of all, we have to say where does our measure live, and I will use a very little measure theory actually. That everybody who has looked at this knows that you need something like a sigma algebra of measurable subsets usually. This is where your measure is defined. Now we have this presheaf, which actually does have subobjects, of course, but these subobjects do not form a Boolean algebra, rather a Hating algebra. So we can expect to have not a sigma algebra, which is a Boolean algebra in particular. We need some Hating algebra instead. And then it turns out that there is a certain kind of subobjects which we call Kochen subobjects. This part I skipped actually. These are not all of them, but there are more subobjects, but we just pick these particular ones, and you should think of these as the analogs of measurable subsets. And they form a complete Hating algebra, and that's good enough for what we want to do with them. Okay, and here's the definition. So if you have one of these quantum states I talked about in the beginning, so if a state on your phenomenon algebra is such a row, you associate a probability measure on the Kochen subobjects in a very straightforward way. So I should maybe say what these Kochen subobjects look like. Well, I always write them as S underlined, and they just have components, one component for every V. And this is just, you should think of this is just every SV is a subset of the Gelfand spectrum of V. Gelfand spectrum was this space where I can write the algebra V as functions on some space. I said this is this Gelfand spectrum, so I take some subset of this space, and actually I take a Kochen subset. This is why these things are called Kochen. And I do this for every V. And then there's this thing, and this is why I take Kochen subsets. Kochen subsets exactly corresponds to projections in V. So I can switch between projections in this abelian subalgebra and Kochen subsets of the Gelfand spectrum. This is why I take Kochen subsets. This is what I do here. I go from SV to PSV is the corresponding projection, which lives in V. And just apply rho to it. I mean, that's the simplest thing I can do. I just evaluate the state on this thing. This gives me a number between 0 and 1. And I do this for all different V's. This means, and this is maybe the one thing that looks a bit odd, that my measure takes values not just in the real numbers. So if I want to say what is the measure of some given subobject S, it's not a single number, it's rather a whole bunch of numbers, only one number for every context. So we could say in this sense it is contextual. I will not speak much about the Born rule. I can say something about the Born rule, how I can extract actually the expectation values from these ones. You get one value for every context. One real number between 0 and 1.
Deterministic.
Sorry?
Is it deterministic or not?
Well, this is on this level. It's basically a mathematical statement. I mean, what do you mean? I mean, it's a quantum state and you evaluate it in a projection. You can say it's the expectation value of the projection. In this sense, it's not deterministic.
Then what's the difference to the Beltrami-Vygotsky model?
The difference is that we will see. Well, first of all, it works. Much more generality works for basically all for non-algebras. But more importantly, we can. Well, there is a good underlying geometric picture. There's this spectral presheaf. I didn't say this too much, but this is this idea that this is a state space, for example, where the physical quantities live as certain, well, not functions anymore, but certain arrows in the topos now. This is all there, so the structure is much stronger than just saying, okay, take Hilbert space with delta peaks on singling out. There's much more geometrical structure here than you would have in such a model. So first of all, the whole of sigma goes to the function which is constantly 1. All these projections up there would become the identity, and then rho on the identity gives me 1. So that's what happens if I have rho, if the empty subobject gives me constantly 0. And I have this property which has to do with how subobjects look like. It just means if I go to a smaller subalgebra, then I can only get a larger number. So this is pretty straightforward. And why do I call it a measure at all? It's basically because of this property. Forget all the stuff. And it's not difficult. If you have two subobjects, then this measure behaves in this way. So mu rho of S1 or S2 plus mu rho of S1 and S2 equals mu rho of S1 plus mu rho of S2. I'm not quite sure if these measures, for example, these probability distributions that you have would fulfill something like this. I'm not entirely sure about this. People from measure theory would see this as an essential feature. Actually, this is just a countable version of it. They would well, this is just a finite version. They would want a countable version of this. It's some kind of regularity condition. But now, all I've been doing so far is saying, okay, you can take a state of a quantum system and you get some of these, one of these measures. I think much more interesting is the other way around. I can say abstractly what such a measure is, and I can get back a quantum state. So I can, in that case, knowing my lambda is exactly knowing my psi, and the other way around. So there are no hidden variables in this sense. There's nothing extra. It's just, but it shows that you can rewrite quantum states in a very general sense as probability distributions, but not living on a set, rather living on this structure, which is a space without points. That's the main
so knowing your lambda means knowing your psi. So I can't see why it has an advantage over something like Beltrami-Vygotsky, which also knowing your lambda is knowing your psi. It's now you know, a well-defined measure on a set. Do you see, in terms of, let's just say, the philosophical aspect of trying to sort of understand the Kochen-Specker theorem, I don't need to have the Kochen-Specker theorem if I take an intrinsically indeterministic theory, like Beltrami.
Well, this.
So.
You go to, well, okay, it's, yeah, this does not become visible because I'm just showing a small part of the story. The thing is, you have lots of other mathematical aspects in this topos descriptions, in particular logical aspects you can talk about. And lots of these questions about probabilities can be shifted, and now we get a logical perspective on them using the internal logic in this topos. So this is where I see a potential also philosophical gain in this whole story. It's not just rewriting something and then ideally, but this is more or less an open question. I would like to see that we can eventually reduce all these probabilistic aspects to purely logical aspects now treated within the logic of this topos.
Could I make a couple of remarks about the sort of quote-unquote probability distributions you
sure.
get? If you sort of think of what a constructive probability theory might be, then you can't directly use the Kolmogorov axioms because sets don't have complements. So the closest thing you have is what you just wrote down. Probability of the union plus the probability of the intersection. And these things actually arise because you get what is normally known as Dempster-Schaeffer theory, which people use in information retrieval. And if you have to actually, associated to a set of an observable, you get basically two numbers. One of which is the probability assigned to it, and the other of which is the probability assigned to its double negation. And in Dempster-Schaeffer theory, those are called inner and outer probabilities, or whatever. So these things do arise, and not just in quantum mechanics. And I think and I think
that's an interesting point. I think it should tie up with some other things.
I think with I think if with a sort of proper attention to the sort of story you're telling about how this stuff correlates with observations.
That's an interesting point. I mean, I was happy when I proved this stuff that I could capture a very general notion of what a quantum state is. But if there are other situations where you have, first of all, a similar situation that negation doesn't work in the standard way, so this is definitely interesting. And do not talk about negation here, and I didn't need it in the proofs, luckily, but clearly it's an interesting question. And, so let me just say what you can prove, actually. We can say absolutely this is a probability measure, so you will see there's no quantum state in this definition. You just say you have a mapping from these measurable sub-objects to, these values between 0 and 1, such that the whole thing goes to constantly 1, and it has this property here. I want to emphasize two things. First of all, this is, it does not refer in any direct way to the non-commutativity of the algebra. So, why doesn't it do so? Well, because all these things that we have are local requirements. I didn't say how this actually is defined, but you define this component-wise at each me, this OR of subjects, this AND likewise. Also this addition. So this is just, this doesn't relate different contexts at all. The only little piece of information relating different contexts, different V's, is that, this codomain here means if you go to a smaller context, you can only assign a larger number. So we have a situation where you may think there must be many more of these than there are quantum states, because a quantum state is a linear function on the full algebra, while this is very, very local and doesn't seem to capture non-commutativity or linearity and all these things. In fact, it does. There is no condition of countable additivity, so some of the measure theory might say, there's no regularity whatsoever, you could want more. I don't need it, and actually I don't even want it, because I want to say something about non-normal states which may not have these additivity conditions after all. Okay, this is what I just said, but still you can show these. If you have for non-algebra, the only exception is it's not allowed to have a summand of type 1, 2. This is basically 2 dimensions is excluded. And you have a measure of the kind I described on sigma, and then there's a unique state of the phenomenon algebra, such that the measure associated to that state is the measure you started from. And so this just means for every phenomenon algebra, without this type 1, 2 summand, there is a bijection between the space of states, this thing I introduced in the beginning, and the set of probability measures on the global sub-objects. And of course, this you can transport the topology from S of n over here. And so it's just a new description. So now you can think about quantum states in a very general sense as being measures on something. But this something is not a set, but rather, well, it's presheaf. And how is it proved? Well, it uses Gleason's theorem. And because we want a coffee break, I'll just skip this. The idea is again as simple as it can be. You just do the following. If you have a sub-object S, and at some context V, you have that this component SV corresponds to projection P. Just say, I define M of P as what the measure gives me there. Then, of course, you have to prove that this is well defined. This is not very clear. You could have some other sub-object which corresponds to P in some other context. And why does it give me the same number? So this needs a proof, but it can be proved. And then you get this M of P, if you do it for all the projections, is what is called probability measure of the projections, and this can be extended to a state. So this is where Gleason's theorem comes in. And also, just the last thing I want to say, normal states, which are quite important, can be characterized very neatly. Being normal is kind of being continuous in a certain way. And it just translates to the following. You measure mu corresponds to the normal state if and only if it preserves joins. It can form joins, which are like unions of these sub-objects. And if likewise, on the other side, you have unions of these values, which are these functions between 0 and 1. And there you take the join in every V. So this is also as simple as it can be. And this just means you can describe the whole pre-dual, basically you can describe the dual space of your phenomenon algebra in terms of these measures in a very straightforward way. Okay, so that's it.
Questions, comments?
So I want to go back to just, as a physicist, why do you find contextuality unnatural? Because I say what Bell would say is, look, it's a different experimental arrangement if I'm measuring my spin components with my magnet oriented like this or like that. The fact that there's, this one projector in common or something, it's actually, classical apparatus is different. And so why object to the theory depending on the full configuration of the objects which are doing the measurements?
Well, the basic reason is that I don't want to think about quantum systems just in terms of measurements and classic configurations of apparatuses. I want to be able to say something about the thing in itself. And I think about such a projector which can show up in different orthonormal bases. This is one yes-no question. I don't see any compelling reason why any measurement which poses this yes-no question should automatically measure a maximal observable which corresponds to a whole orthonormal basis. I mean, why should that be the case? Why can't I just ask this question, and if you give me that, why on earth should it correspond to, why should it depend on
Because if you try and do an experiment which only has two outcomes, has that projector and identity minus that projector, it's actually, go into a lab downstairs and you have to build a completely different apparatus to do that measurement. It's actually, if we could do those measurements, quantum computing would be much easier than what it is. It's much easier to do sharp ones. So there are people devoting millions of dollars to build an apparatus to do measurements onto degenerate subspaces. And so I know that they're physically a different measurement. And so why should I be surprised if in my theory, I treat that apparatus differently to the apparatus which does the full set of projectors?
Well, the thing is, we do not want to circumvent I sometimes say we want to circumvent the Kochen-Specker theorem, something like this. It's not actually true. Of course, the Kochen-Specker theorem, well, it holds in the sense that, okay, you can't do certain things in a non-contextual way.
Can you explain to us what this theorem that you keep referring to is?
Oh, the Kochen-Specker theorem. Oh, yes. Okay. what's the best formulation? There are different formulations of that.
Doesn't
So-
have to be technical, non-technical.
Yeah, so you take your, well, in this case, all bounded operators on Hilbert space and take the self-adjoint operators among them, or more generally for normal algebra and the self-adjoint operators in there. You ask, is there a mapping from the self-adjoint operators to the real numbers such that every operator is assigned one element of its spectrum? And secondly, if one operator is a function of the other, let's say B equals f of A, then the requirement would be the value assigned to B is f of the value assigned to A. So, make it simple, let's say the functions are taking the square. So you would expect that to the operator A squared to assign the square of the value that you assign to A. And then the theorem says there are no such functions from the self-adjoint operators to the real numbers. So you cannot, and this has a mathematical reason, this does not depend on any physical interpretation.
But
So you cannot assign values to all physical quantities at once. You cannot use the quantum state to do so, this was well known. Kochen-Specker basically asked, are there other mathematical devices which would do the trick? And then you can show it's not possible. And it is equivalent to saying there cannot be a space such that the physical quantities become real valued functions on this space. And this space carries a measure, and this measure then gives me all the predictions that quantum theory gives. So people usually say it's a theorem about hidden variables. Actually, it's a theorem about hidden states. It rules out certain hidden states models, because it says, okay, you cannot have a set like the state space in classical physics and the physical quantities as functions thereon, and the measure which gives you the predictions of quantum theory. So it's a no-go theorem, as a negative.
Crude philosophical implication of that is that nature is sort of inherently probabilistic, because there's no sort of underlying stochastic model you could produce. But then there are these dodgy issues of the assumptions in that theorem, like that's this contextuality we discussed.
Yes, this has to do very much with the question. This contextuality comes in actually with the fact that, well, you can have that one operator, let's say B is a function of A, some operator A, but at the same time it's also another function of another operator C. For example, this projection, well, Terry had these pictures. Let's say this projection onto this line here, this is our operator B. The operator A is associated with this orthonormal base, and there's another orthonormal basis of this kind. This is associated with the operator C. Then I can get the operator B as a function both of A and C as written here. And the important thing is that A and C do not have to commute. They both, well, A commutes with B and C commutes with B, but A doesn't have to commute with C. So commutativity is not transitive in this sense. And this, well, then people start calling, well, there's such an orthonormal base, and this is one context, and this other orthonormal base is another context. And I think, and that's actually the question we're discussing here, it is natural to say, okay, but the thing they have in common, well, Terry insists, okay, this corresponds to one experimental setup, or this corresponds to another experimental setup, and I shouldn't even think about having them something in common.
No, it's not that I don't think they should have something in common.
Okay.
And I think that certainly the deeper physical understanding of what properties are being measured would make that easier.
Yeah.
It's just that I don't think it's unnatural. Even like with the classical example of the charges on stick, it's not unnatural for the results of measurements to depend on the actual configuration of the apparatus. You cannot build two apparatuses which are physically the same and which both measure those two different things.
I think we should maybe wrap up and then...
I just want to make one comment here. So Andreas doesn't like complexity, doesn't really care about these overlaps of Terry. Terry doesn't like non-overlapping ones, doesn't care about contextuality. If you actually put both of them together, like you don't care about the overlaps and you don't care about contextuality, it's trivial to build hidden variable models. So somebody who is broad enough to sort of encompass both of these guys, and he has no problem whatsoever.
So maybe we should care less. Yeah?